Welcome back, AP Stat. We're going to be solving problems by finding cutoffs to start our last of 4 sections of Chapter 5. So, suppose a college says it admits only people with SAT verbal test scores among the top 10%. How high a score does it take to be eligible? We're going to recall that verbal test scores have a mean of 500 and a standard deviation of 100. First, we check the nearly normal assumption applies, namely that the data are unimodal and symmetric. We're going to state the model we're using in this correct format. Then we sketch the annotated curve modeling the scenario and then perform the calculation and state the results. Right? So here's how we would start. Okay? So since the data are unimodal and symmetric, I can use this normal model. And we sketch it down here. We want to find this cutoff here that's going to cut off the top 10% of scores. And we're going to need to use the graphing calculator to do that. And here we are back at the calculator. I'm going to go to second distribution. We're going to go to inverse norm, number 3, and we are going to enter in the relevant information. Now, I want the top 10%, which means that I'm not going to enter 0.1. I'm going to enter the complement 0.9. Okay, I'm going to enter 0.9 because inverse norm finds a cutoff for a probability below. If 90% would be below our cutoff, then 10% is above. Okay, got to keep that in mind when using inverse norm. Again, as I've said before, if you have a new calculator, you can just put the 0.1 there and say right. Okay, makes it really easy on you. Here we have the mean. The mean is going to be 500, and the standard deviation will be 100. And we click paste. And there is our answer, 628.155 approximately. So to score in the top 10%, we would need at least a score of 630. Now, why do I say 630? Well, the answer is about 628. 628.155 is what I got on the calculator approximately. But for the SAT, only multiples of 10 are possible scores. We know that a 620 would be too low, so we would say 630 and up would get us in that top 10%. Okay, let's move into a several-part application of basically everything we've been talking about. A cereal manufacturer has a machine that fills the boxes. Boxes are labeled 16 ounces, so the company wants to have that much cereal in each box, but because no packaging process is perfect, there will be minor variations. If the machine is set at exactly 16 ounces and the normal model applies, or at least the distribution is roughly symmetric, then about half the boxes will be underweight, making consumers unhappy and exposing the company to bad publicity and possible lawsuits. It's cereal, people. Anyway, to prevent underweight boxes, the manufacturer has to set the mean a little higher than 16 ounces because people are crazy about their generic-looking cereal. Anyway, based on its experience with the packaging machine, the company believes that the amount of cereal in the boxes fits a normal model with a standard deviation of 0.2 ounces. The manufacturer decides to set the machine to put an average of 16.3 ounces in each box, so a little bit extra on average. Let's use that model to answer a series of questions about these cereal boxes. Okay, so first we check to make sure the nearly normal assumption applies, and we see that pretty clearly. We see that the distribution is roughly symmetric and that the normal model applies. So we can check off that box, as it were. Then we're going to state the model we're using. This is normal, mean, and sigma. We need to figure out what the mean and the standard deviation are. Very good. Then we sketch the annotated curve modeling the scenario and perform the calculation and state the results. So since we know the nearly normal assumption applies, Feel free to pause the video and try to do these last 3 on your own, or you can just watch me do the last 3 steps. Okay, I'll assume we're ready to continue. Very good. So, since the data are unimodal and symmetric, as we've said before, I can use the normal model centered at 16.3, that's what we've set the mean to, and a standard deviation of 0.2, right? If I were to find this probability over here, that would be 0.067 or 6.7% of the boxes being underweight. Why this cutoff right here? Well, because anything below 16 ounces is going to be underweight. Here's my mean. I want the odds of being below 16 ounces, and that probability is about 6.7%. And I'll show you how to do it on the calculator. So we're here at the graphing calculator, and I have the normal CDF up, or finding a probability given a cutoff. We have our arbitrarily low number here. There's no bottom cutoff. The upper cutoff would be 16, and mean is 16.3, standard deviation is 0.2. Time to hit paste and let the calculator do the rest. And there you go, about 6.7%. Okay, so the next part of this problem will require a bit more ingenuity. Question 2. All these details are the same. Question 2. The company's lawyers say that 6.7% is too high. Let me tell you, working for this company must be stressful. It's a cereal company, for goodness sakes. They insist that no more than 4% of the boxes can be underweight. Okay, we got standards here. So the company needs to set the machine to put a little more cereal in each box. What mean setting does it need? So let's break down what's going on. Clearly the nearly normal assumption is going to apply, and we are going to be using a normal model, but this time we don't know the mean, but we still do know the standard deviation. It's going to be 0.2 ounces. We don't know the mean, though. The mean is actually what we have to adjust given a cutoff, okay? And we want this cutoff to be positioned such that this area is 4%. That's where this 4% comes into play. If no more than 4% of the boxes can be underweight, the odds of being underweight can at most be 4%. So what does the mean have to be? How do we adjust our machine to make this area go from 6.7% down to 4%? That is going to involve us performing a calculation stating the results. And the way we're going to do that is consider what z-score is going to keep 4% of the area below and use that z-score to find the mean. So I'm actually going to find a standard score using the calculator. I'll show you how to do it. You can try and do it on your own, but this is a little tricky. I encourage you to just watch me do this one. Okay? You can try it if you like, but let's do this in the calculator. So we're back in the calculator. Very good. For area here, I am going to say 0.04. Okay, so I want to find the cutoff such that the area below is 0.04. Now here's the tricky part. What do I set for the mean and the standard deviation? Well, let's think about what we know about standardized data. We want to find a standard score, okay? And for standardized data, the mean is going to be 0. And the standard deviation is going to be 1. So if you want to find a standard score that would put a certain amount of area above or below it or whatever, you just keep the mean and standard deviation 0 and 1 respectively, and you're good, okay? And we get negative 1.75 approximately, which is the estimation that we will use. So we're back to the problem. First, we're going to state the model that we're using since we know the nearly normal assumption applies. We will use this model right here. It is a normal model. We don't know the mean. That's the whole point of this problem, but we do know the standard deviation, and that's going to be extremely helpful. This is an annotated curve modeling the scenario. The book likes to put a little flag right here. I get why they do that. They want to draw attention to this being the cutoff. I think it's a little cheesy, but I don't have a doctorate in statistics, so what do I know? Anyway, here's our annotated model right here. And now I'm going to employ that negative 1.75 value. Here we go. So you remember the formula. Standard score Z is equal to X minus the mean over the standard deviation. Okay? Let's look at what values I know. I know the standard score that's going to get me an area of 0.04 is negative 1.75. Calculator told me so. The value I want to be below is 16. So that's going to be my value for X. All right, that's my data value where I have my cutoff. The mean I don't know, and the standard deviation is going to be 0.2. From here, it's just algebra. I would multiply both sides by 0.2 to undo the division, and then I would subtract a 16, then divide by a negative 1. If you do the algebra correctly, you will get mean is equal to 16.35, which is the answer to the question. So, how do I make sure that no more than 4% of the boxes can be underweight? Well, I need to set the mean to 16.35. That'll keep the percent of boxes that are underweight within the acceptable range. One more problem in the series. The company president vetoes that plan. Whoa. Saying the company should give away less free cereal, not more. Her goal is to set the machine no higher than 16.2 ounces and still have only 4% underweight boxes. The only way to accomplish this is to literally change the only thing that we haven't touched so far, which is the standard deviation. What standard deviation must the company achieve, and what does that mean about the machine? Okay, so this is going to be similar to the style of the last problem. Okay, so I'm going to give you a chance to try this one on your own. We know the nearly normal assumption applies. No need to restate that. We state the model we are using. You can take a chance to try your hand at that. Sketch the annotated curve modeling the scenario. Here's my new mean. Here's my cutoff. The little flagpole that they put up there. It's giving me some end of the level Super Mario vibes now that I think about it. All right. Perform the calculation and state the results. We know the z-score with 4% below is negative 1.75. We'll incorporate that, and we're also going to incorporate the mean of 16.2 and the value 16 here. So take a moment. I want to see if you can figure this out. Try this one on your own and see if you can find what standard deviation would give us, with a mean of 16.2, 4% boxes underweight. All right, I'll assume we're ready to go on. Here we go. So there's my model we're going to use. And here is the math. This is the interesting part. We have the z-score that gets 4% below. We have our data value, our cutoff. We have the mean, and we have the standard deviation, which is unknown. Both a little algebra, we can know it. Here's how we do it. I could subtract 16.2 from 16. I would get 0.2. Then I could multiply both sides by sigma, divide both sides by negative 1.75. If I were to do that, I would get approximately 0.1143. So my standard deviation would have to be a bit smaller to make a mean of 6.2, a curve with a mean of 6.2 only generate a value below 16 4% of the time. The last topic in this section is going to be the normal probability plot. In a normal probability plot, each datum, that's the singular for data, is plotted with its value on the y-axis and its z-score on the x-axis. If the distribution of the data is approximately normal, the plot will by and large resemble a diagonal straight line. So what we're doing is we're taking data that could be graphed like this. This is very bell curve-ish. And we take each of the data values and we find their normal scores. Okay, so we standardize the data. We would take each data value, subtract the mean, and then divide that by the standard deviation. If we do that, by and large, we get a straight line. Yeah, there are some stragglers over here, some interesting characters over here. By and large, it's a straight line that really bulks up in the middle because our data bulk up in the middle. However, the normal probability plot of a variable that fits a skewed distribution won't have that straight diagonal line. So again, we have our histogram that is obviously right skew, and we have our normal probability plot that says just as much. The data appear to be bulked on the lower end, just as we expect from our distribution here. What a normal probability plot says about the distribution. You can look at a normal probability plot and you can tell how the data are distributed a lot of the time. Sometimes it's not as clear, but here in these two instances, it's pretty clear. Now you know a straight diagonal line means the data are symmetric. And if it's bulked in the middle, like in this example, it's going to be unimodal and symmetric. That's a really ideal circumstance in stats. But if we have something that looks like this, the data are going to be right skew. The plotted points appear to bend up to the left of the normal line, indicating a long tail to the right. Okay? So if our data are bulked on the lower end, we're going to have points that start going like this, and we'll have the normal probability plot would dip below the line that would indicate our data are symmetrical, and then it'll come back up this way. And I'll let you think about why that's true. By contrast, left skew, the plotted points appear to bend down to the right of the normal line, indicating a long tail to the left. So if I have a left skew curve like this one, most of the data are going to be on the right. So our probability plot is going to look like this. Here's the normal line. We start below, we inch up to around that normal line, and we may cross it around here, and then we start drifting to the right. And again, I'll let you think about why that is true. So here's an example of how you can create a normal probability plot on the calculator. I input some values into list 1. I'm going to go to stat plot, and I'm going to change plot number 1 to this guy. I'm going to keep going right, and that'll take me to my normal probability plot. Okay? The data list I'm using is list 1. Data axis. To make it look like the one that I just showed you, you need to make your data axis Y. That means that the z-scores for each data value will be plotted on the x-axis. And you can choose how the points are marked. I like the one that's automatically selected. Now you can go to Zoom, hit number 9 for Zoom Fit, or not Zoom Fit, Zoom Stat. Hit number 9 for Zoom Stat, and there you go. There's your normal probability plot. So I don't see that much curvature in this plot. So I'm going to guess that these data are unimodal and symmetric. We can check ourselves by going to second stat plot, and we can open up plot 1, and we can just change it to a histogram and see what we get. So go to Zoom, number 9 is Zoom Stat, and there you have it. That's looking pretty unimodal and symmetric to me. Yeah, there's that one dip right there, but that's okay. These are real world data, most likely. So it's not going to be perfect, but that's pretty unimodal and symmetric if you ask me. And this looks to me like a nice homework assignment. Have a go at this. Looking forward to working with you on this homework assignment when we return to class.